All right, let's dive into this deep dive on the photoelectric effect.
Yeah, sounds good.
It's one of those physics topics that I was found kind of fascinating, but also a little bit head-scratching.
Oh, absolutely. It definitely challenges some of those common assumptions we have about light and how it behaves.
And luckily for us, we've got a great source to help us unpack it all. We've got this educational website, and it's got this awesome interactive simulation. So
Oh, simulations are fantastic.
they really are. I mean, they can really make these abstract ideas way more concrete and easier to grasp, wouldn't you say?
Absolutely, especially with something like the photoelectric effect where you're dealing with, things happening at the atomic level.
Right, exactly. It's
Yeah.
not like we can just, see those photons knocking those electrons loose with the naked eye.
Exactly.
So this website, it starts with a simple definition. It says the photoelectric effect is when metals emit electrons when light shines on them.
Right, a nice and concise way to put it. But of course, as with most things in physics, there's a bit more to it than that.
There always is.
Right. And it's really this more to it that makes it so darn interesting.
Okay, so spill the beans. What's the catch?
Well, the key here is that it's not just ANY light that causes this effect.
Ah, I see.
There is a very specific threshold frequency that the light needs to have in order for those electrons to actually be emitted.
So it's not just about how bright the light is.
No, not necessarily. You could have a super bright light, but if the frequency is too low, nothing's going to happen.
Hmm, that's counterintuitive. Like, I would have assumed brighter light, more energy, more electrons popping out.
Right, it seems logical, but that's where the whole particle nature of light comes in, you see.
Okay, so this is where it starts to get a little mind-bendy, right?
Exactly. So for a long time, scientists thought light only behaved like a wave, like ripples in a pond.
Yeah.
But the photoelectric effect threw a wrench in that whole idea because it showed that light can also act like it's made up of these tiny little packets of energy called photons.
Okay, so like little bullets of light.
That's a good way to think about it, yeah.
So if those photons don't have enough energy, those electrons are staying put.
Exactly. It's like trying to knock down a bowling pin with a ping pong ball. No matter how many you throw, it's just not going to happen.
Okay, I think I'm starting to get the picture here.
Good, good. Because this is really the foundation of understanding the whole photoelectric effect.
So the website mentions some learning goals, and one of them caught my eye. It says, understanding the equation EF.
Ah, yes, the famous equation that describes the energy of a photon.
Could you break that down for us a little? I mean, I remember seeing that in my physics class, but
Sure, no problem.
yeah.
So E stands for energy, that's the energy of the photon. F stands for frequency, which is, as we were talking about, how many waves of light pass a point in a given time. And H is Planck's constant, which is just this fundamental constant in physics.
Right, I vaguely remember Planck's constant. So a higher frequency means a higher energy photon.
Exactly. And that's how it all ties back to that threshold frequency we were talking about. If the frequency is too low, the photons just don't have enough energy to kick those electrons out of the metal.
It's like they don't have enough oomph.
Precisely. They need that extra kick to overcome the forces holding those electrons in place.
So this seemingly simple effect really challenges what most of us think we know about light, right?
Oh, absolutely. And, this was actually a huge turning point in physics.
I bet.
It really led to the development of quantum mechanics, which is this whole new way of looking at how the universe works at the smallest scales.
So this tiny little effect opened up this massive new field of science.
Pretty much, yeah.
And, what I love about this website is that they don't just tell you about the photoelectric effect, they actually let you play around with it.
You're talking about the interactive simulation, right?
Exactly. And it's not just for, computer nerds. This thing runs on phones, computers, even Chromebooks. Anyone can access it.
I love that. It makes learning so much more accessible.
Right. And what's even cooler is that they provide the actual embed code. So you can, put this simulation on your own website.
Oh, wow. That's amazing.
Right. So if you wanted to, jazz up your blog or
Oh,
something.
I have to try that. But what's great about simulations in general is that they let you, mess around with the variables.
Yes, you can see what happens when you change this or you tweak that, and it's all happening in real time.
Way more engaging than just reading about it in a textbook.
Totally. And it really helps you get a feel for how the different parts of the photoelectric effect all fit together.
It makes it much more intuitive, that's for sure.
So have you had a chance to play around with this particular simulation yet?
I have, yeah. And I have to say, it's really well designed.
I'm curious to hear more about that. But first, I want to touch on something you mentioned earlier. This whole idea that the photoelectric effect really shook things up in the world of physics.
Oh, yeah, it was a real game changer.
So, before we dive into the specifics of the simulation, can you paint us a picture of what the scientific landscape was like before this effect came along? What was the understanding of light at the time?
Well, back then, the dominant theory was that light was purely a wave.
Okay, so like those ripples in a pond we talked about?
Exactly. And this wave theory, it had done a pretty good job of explaining a lot of things about light, like how it bends around corners or creates interference
All
patterns.
seemed to make sense, right?
Right. But then along came the photoelectric effect, and it started to poke some holes in that neat little picture.
So there were some cracks starting to show in the foundation.
Yeah, you could say that. Because the wave theory just couldn't explain certain aspects of the photoelectric effect, like why the intensity of the light didn't always matter.
Right, it was all about the frequency like
Hmm.
we discussed.
Exactly. So there was this growing sense that something was missing, that there had to be more to the story of light than just waves.
And that's where Einstein stepped in with his revolutionary idea.
He did. And, it wasn't just some random guess. Einstein's idea about light behaving like a particle, it actually built upon the work of other physicists like Max Planck.
So it wasn't just a sudden eureka moment, it was more like a gradual evolution of ideas.
Right, exactly. Science is often like that. One discovery builds upon another, leading to a more complete understanding of the world around us.
And in this case, that more complete understanding involved accepting that light can be both a wave and a particle,
Yep, that's the mind-blowing concept of wave-particle duality.
a concept that we owe in part to this seemingly simple effect of shining light on a metal and seeing electrons pop out.
Isn't it amazing how something that seems so basic can unlock such profound truths about the universe?
It really is. And it makes you wonder what other everyday phenomena might be hiding equally profound secrets, just waiting to be discovered.
Now that's a question to ponder.
It is. And maybe we'll find some answers in the next part of our deep dive. But before we get there, I'm itching to hear more about this simulation. What makes it so special? What can you do with it? How does it bring the photoelectric effect to life?
Well, first of all, it's incredibly user-friendly.
Even I can handle it.
Even you! Trust me, it's very intuitive. You don't need to be a physics whiz to navigate it. You can easily adjust all sorts of parameters, like the frequency and intensity of the light source.
So we can actually test out what we've been talking about. Like, we can change the frequency and see if it affects the number of electrons being emitted.
Exactly. You can see for yourself how that threshold frequency works. And you can play with the intensity too, see how more photons affect the outcome.
So it's like having a virtual lab at our fingertips.
That's a great way to put it, and it gets even better. You can also change the type of metal being used in the simulation.
Oh, that's interesting. Does that make a difference?
Absolutely. Different metals have different work functions, which is the minimum amount of energy needed to eject an electron from the metal's surface.
So some metals are clingier to their electrons than others.
Exactly. And the simulation lets you see how that plays out. You can switch between different metals and observe how the threshold frequency changes accordingly.
That's a cool way to see how the work function influences the effect.
It really is. And you know what else is cool? The simulation allows you to apply a voltage to the system.
A voltage? What does that do?
Well, remember how we talked about those emitted electrons having kinetic energy?
Yeah, they're like tiny little projectiles zooming away from the metal.
Right. Well, by applying a voltage, you can create an electric field that can either help or hinder the motion of those electrons.
So you can basically give them a boost or put on the brakes.
Exactly.
Yeah.
And by adjusting the voltage just right, you can actually stop those electrons dead in their tracks, even if they have enough energy to escape the metal.
Wow, that's amazing. It seems like this simulation really does give you a deep understanding of how the photoelectric effect works.
It really does. And the best part is it's all interactive and visual. You're not just reading about it, you're actually seeing it happen, which makes it much more engaging and memorable.
I'm sold. We'll definitely have to include a link to this simulation in the show notes so our listeners can check it out for themselves. But before we move on, I want to touch on something else that really fascinates me about the photoelectric effect. It's not just about the science itself, it's about the historical context. How this one discovery really shook up the scientific world.
Oh, absolutely. It was a paradigm shift, no doubt about it.
So, take us back in time a bit. What was the prevailing view of light before the photoelectric effect came along? What did scientists think they knew about light?
Well, as I mentioned earlier, the dominant theory was that light was a wave. And this wave theory had been very successful in explaining many observed phenomena, like diffraction and interference.
So it seemed like a pretty solid theory.
It did. It fit the available evidence quite well. But, science is all about constantly testing our understanding of the world. And as scientists conducted more experiments, they started to find some discrepancies, some things that the wave theory just couldn't explain.
And one of those things was the photoelectric effect.
Exactly. The wave theory predicted that the energy of the emitted electrons should depend on the intensity of the light, but experiments showed that it actually depended on the frequency.
So brighter light didn't necessarily mean more energetic electrons.
Nope. That's where the wave theory broke down. It simply couldn't account for that observation.
And that's where Einstein's genius came in.
Right. He proposed this radical idea that light could also behave as a particle, a photon, and that the energy of each photon was directly proportional to its frequency, not its intensity.
So he essentially married the wave and particle views of light.
In a way, yes. He didn't completely discard the wave theory, but he added this new layer of understanding, this idea that light could also exhibit particle-like behavior.
And that new layer of understanding revolutionized physics, leading to the development of quantum mechanics.
It was a huge leap forward. And it all started with a seemingly simple observation about light and electrons.
It's a reminder that sometimes the most profound discoveries come from the most unexpected places.
Absolutely. And it highlights the importance of being open to new ideas, even if they challenge our existing assumptions.
Well said. So we've covered a lot of ground in this first part of our deep dive. We've explored the basics of the photoelectric effect, its historical context, and even touched on its real-world applications. And we've learned that sometimes the most seemingly simple phenomena can unlock profound truths about the universe.
It's all about asking the right questions and being willing to explore the answers, no matter where they lead.
And speaking of exploring, I'm really eager to dive into that interactive simulation. I think it'll bring all these concepts to life in a whole new way.
I agree. Let's get to it. So, as we were saying, this simulation really lets you get your hands dirty with the photoelectric effect.
I'm ready to get my hands dirty. Show me what this thing can do.
Okay, so first of all, you can adjust the frequency of the light.
Okay, and that's important because, like we talked about, the frequency determines the energy of those photons.
Exactly. And the simulation lets you see how that affects the number of electrons emitted. You can crank up the frequency and watch those electrons start flying off the metal.
So we can actually see that threshold frequency in action?
You got it. You'll notice that if the frequency is too low, nothing happens, no matter how bright the light is.
Right, because it's all about the energy of those individual photons.
Precisely. And the simulation really drives that point home.
Cool. What else can we tweak?
Well, you can also adjust the intensity of the light.
Which means we're changing the number of photons hitting the metal.
Exactly. And you'll see that if the frequency is above the threshold, increasing the intensity will cause more electrons to be emitted.
Because more photons means more chances to knock those electrons loose.
Exactly. But remember, if the frequency is below the threshold, even a super bright light won't do anything.
Right, because those individual photons just don't have enough energy to get the job done.
That's the key takeaway here. Frequency is king when it comes to the photoelectric effect.
Okay, I'm starting to feel like a photoelectric effect expert already. What else can this simulation do?
Well, it also lets you change the type of metal being used.
Oh, interesting. Does that matter?
Absolutely. Different metals have different work functions, remember?
Right, that's the minimum energy needed to pry an electron away from the metal.
Exactly. And you can see how that affects things in the simulation. You can switch between different metals and see how the threshold frequency changes.
So some metals are more stubborn than others when it comes to giving up their electrons.
That's a good way to put it. Metals with higher work functions require more energetic photons to trigger the photoelectric effect.
Makes sense. So this simulation really lets you explore all those nuances of the photoelectric effect.
It does. And it's not just about playing around and seeing what happens. You can actually make measurements and collect data.
Oh, really? Tell me more.
Well, for example, you can apply a voltage to the system.
Oh, voltage. What does that do?
Well, it creates an electric field that can either help or hinder the emitted electrons.
So you can basically give them a boost or slow them down?
Exactly. And by carefully adjusting the voltage, you can find the point where the electrons are completely stopped.
So you're like putting on the brakes for those electrons.
That's a good analogy. And the voltage required to stop those electrons is a direct measure of their kinetic energy.
Wow, that's pretty clever. So this simulation isn't just a toy, It's a legitimate scientific tool.
It is. You can use it to explore the photoelectric effect in a very hands-on way and even collect data to support your understanding.
I am seriously impressed with this website. They've really done a great job of making this complex topic accessible and engaging.
I agree. It's a testament to the power of educational technology.
And, it makes me think about all the real-world applications of the photoelectric effect that we mentioned earlier, like solar panels, for example.
Right. Solar panels are essentially harnessing the power of the photoelectric effect to convert sunlight into electricity.
So every time I see a solar panel, I can think about those little photons knocking electrons loose and creating a flow of current.
Exactly. It's a perfect example of how something that might seem very abstract actually has a very tangible impact on our lives.
It's amazing to think about. And it's not just solar panels, right? But you mentioned other applications too.
Oh, yeah, there are tons. Digital cameras use the photoelectric effect to capture images. Night vision goggles rely on it to amplify faint light. And certain medical imaging techniques use it to detect and diagnose diseases.
It's mind-blowing how something that started with a simple experiment shining light on a metal plate has led to so many technological advancements.
It really is a testament to the power of scientific curiosity and ingenuity.
You know, thinking about all these applications makes me appreciate the work of the scientists who first discovered and explained the photoelectric effect even more.
Absolutely. It was a major breakthrough in physics, and it all started with careful observation, experimentation, and a willingness to challenge existing ideas.
So what was the scientific landscape like back then when the photoelectric effect was first observed? What was the prevailing view of light at the time?
Well, like I mentioned before, the dominant theory was that light was a wave. And that theory had a lot of evidence to support it. It explained things like diffraction, interference, and polarization very well.
So why was the photoelectric effect such a problem for the wave theory?
Because the wave theory predicted that the energy of the emitted electrons should depend on the intensity of the light, but that's not what experiments showed.
Right, it was the frequency that mattered most.
Exactly. And that just didn't make sense according to the wave theory. It was a real head scratcher for the physicists of the time.
So what did they do? How did they try to reconcile this discrepancy?
Well, some scientists tried to tweak the wave theory to make it fit the observations, but no matter how they twisted it, it just didn't quite work.
So the photoelectric effect was like a square peg trying to fit into a round hole.
You could say that it just didn't belong in the framework of classical physics.
And that's where Einstein came in with his revolutionary idea.
He did. Einstein, being the brilliant mind that he was, wasn't afraid to think outside the box.
And he proposed that light could also behave as a particle.
Exactly. He called these particles photons. And he said that the energy of each photon was directly proportional to its frequency.
Which explained perfectly why the frequency of the light was so important in the photoelectric effect.
Precisely. Einstein's idea, while radical at the time, solved the puzzle that had stumped physicists for years.
And it opened the door to a whole new world of understanding about the nature of light and matter.
Exactly. It led to the development of quantum mechanics, which has had a profound impact on practically every field of science and technology.
It's amazing to think about the ripple effects of that one discovery.
It really is. And it all started with a simple experiment and a willingness to question the status quo.
It's a powerful reminder that even the most basic observations can lead to groundbreaking insights.
You never know where curiosity might lead you.
Well, our curiosity has led us on quite a journey today, exploring the photoelectric effect in all its fascinating detail.
It's been a fun ride. We've covered a lot of ground, from the basic concepts to the historical context and the real-world applications.
And I think we've both gained a deeper appreciation for this amazing phenomenon.
I know I have. And I hope our listeners have too.
Speaking of our listeners, I'm sure they're eager to check out that interactive simulation we've been raving
I
about.
bet they are. We'll be sure to include a link in the show notes.
Great idea. Now, before we wrap up our deep dive, I want to take a moment to highlight some of the other resources that this fantastic website has to offer.
Yes, they've really gone above and beyond in providing a wealth of information on the photoelectric effect.
You mentioned earlier that you were particularly impressed with a video by Frank McCulley. What is it about his approach that you found so engaging?
Well, Frank McCulley has a knack for explaining complex scientific concepts in a way that's both clear and entertaining. He doesn't dumb things down, but he also doesn't get bogged down in jargon.
So he strikes a good balance between rigor and accessibility.
Exactly.
Yeah.
And he uses great visuals and analogies to help you really grasp the concepts. His video on the photoelectric effect is no exception. He does a fantastic job of breaking down the key ideas and illustrating them in a way that's easy to understand, even if you don't have a background in physics.
That sounds like a perfect resource for our listeners who want to delve a little deeper into the topic.
I highly recommend it. And there are other great resources on the website too, including links to other simulations and articles written by experts in the field.
So it's like a one-stop shop for all things photoelectric effect?
Pretty much, it's a great starting point for anyone who wants to learn more about this fascinating phenomenon.
Well, we'll definitely be sure to include links to all of those resources in the show notes.
Excellent, and I encourage everyone to check them out. You never know what new insights you might gain.
So as we wrap up our deep dive into the photoelectric effect, I want to leave our listeners with a final thought.
Fire away.
We've seen how a seemingly simple observation, shining light on a metal plate, can lead to profound discoveries that change our understanding of the universe. It makes me wonder, what other everyday phenomena might be hiding equally amazing secrets, just waiting to be uncovered?
That's a great question to ponder. It's a reminder that the world is full of wonder and that there's always more to learn.
So stay curious, keep exploring, and never stop asking questions. Who knows what incredible discoveries you might make?
Well said. And on that note, until next time, keep those minds curious. You know, it's amazing how much ground we covered in exploring the photoelectric effect.
Right. And to think, it all started with just that simple question. What happens when light shines on metal?
And look where it led us. A deep dive into quantum mechanics, technological advancements, and even philosophical musings about the nature of reality.
It's a testament to the power of curiosity and the interconnectedness of knowledge. Who would have thought that something as seemingly mundane as shining a light on a metal plate could unlock such profound secrets about the universe?
It really highlights how much we still don't know and how much there is left to discover.
Exactly. So before we wrap up our deep dive, let's take a moment to recap some of the key takeaways for our listeners.
Sounds good to me. Where should we start?
Well, I think the most fundamental point is understanding what the photoelectric effect actually is. It's the phenomenon where electrons are emitted from a material, typically a metal, when light shines on it.
Right, and it's not just any light that can do this. The light has to have a frequency above a certain threshold, which is different for different materials.
That's because the energy of light is delivered in these discrete packets called photons, and the energy of each photon is directly proportional to its frequency.
Thanks to Einstein's brilliant insight, we know that if the frequency of the light is too low, the photons simply don't have enough energy to knock those electrons loose, no matter how intense the light is.
It's like trying to break a rock with a hammer. If you don't hit it hard enough, it doesn't matter how many times you swing.
Exactly. And that's why the photoelectric effect was such a puzzle for classical physics, which couldn't explain why the intensity of the light didn't always matter. It was a real head-scratcher until Einstein came along and proposed his theory of light, quanta.
And that theory, of course, revolutionized our understanding of light, leading to the development of quantum mechanics and all its amazing implications.
It's one of the most profound scientific revolutions in history, and it all stemmed from this seemingly simple observation about light and electrons.
It's mind-blowing to think about.
Mm.
And speaking of mind-blowing, we also explored the concept of wave-particle duality, this idea that light can exhibit both wave-like and particle-like behavior.
Which is another one of those things that really challenges our everyday intuition about how the world works.
Right? Our brains like to put things into neat little categories, but nature doesn't always play by those rules.
And that's what makes it so fascinating. The photoelectric effect forced us to confront this duality and to embrace a more nuanced understanding of light.
It's a reminder that the universe is full of surprises and that there's always more to learn.
Absolutely. And the learning doesn't have to stop here. We've talked about some fantastic resources available online, including that interactive simulation that lets you play around with the photoelectric effect and see how it works in real time.
That simulation is definitely a must-try for anyone who wants to get a more hands-on understanding of the topic.
And don't forget about the video by Frank McCulley that I mentioned. He does a fantastic job of explaining the concepts in a clear and engaging way.
Yes, his video is a great complement to the simulation and the other resources available on the website.
I highly recommend checking them all out. It's a treasure trove of information on the photoelectric effect.
So as we wrap up our deep dive, I want to leave our listeners with a final thought to ponder. If something as seemingly simple as shining light on a metal plate can lead to such profound discoveries, what other mysteries are out there waiting to be uncovered? What other everyday phenomena might hold the key to unlocking even deeper secrets about the universe?
That's a fantastic question, and I think the answer is countless. The world is full of wonder and mystery, and it's up to us to explore it, to ask questions, and to never stop learning.
Well said. So, to all our listeners, stay curious, keep exploring, and who knows, you might just be the one to make the next groundbreaking discovery that changes the way we see the world.
And until next time, keep those minds engaged and those questions flowing.